Welcome to the Deep Dive. We're here to pull out the key insights you need to stay informed. Today, we're tackling something really fundamental to AI. Have you ever wondered why you can give the exact same raw data to different people or different teams, right?
Yeah.
And they train an AI model, but the results are just wildly different. Like some models end up being incredibly accurate, really useful, and others, well, let's just say they're not quite hitting the mark. Maybe glorified paperweights.
Oh, yeah, that's a super common thing. It can be really perplexing, can it? And what's fascinating, often the big difference isn't actually the AI model they chose. It comes down to something earlier in the process, a really critical step, maybe underestimated sometimes. We call it feature engineering.
Feature engineering. Okay, to help everyone listening get a handle on this, let me try an analogy. Think about cooking. Imagine you get a basket, exact same ingredients inside. Tomatoes, a whole chicken, some potatoes, still need peeling. Now, give that same basket to two different chefs. A really skilled chef, they're not just going to dump it all in a pot. No, they'll pick the right cuts of chicken, dice the potatoes just so, maybe roast the tomatoes, add the perfect seasonings. The result, something delicious, works perfectly. But the other chef, maybe they just hack at it, choose bits randomly.
Right.
Even with the best oven, the best kitchen gear, that second meal, probably not going to be great.
That's a brilliant analogy, actually. That ingredient preparation you mentioned, it's absolutely crucial. It's how you turn that raw stuff, the data, into something the AI can actually understand and learn from effectively. And that transformation, that is feature engineering. That's what we're diving deep into today.
Okay, so that's our mission for this deep dive. We're going to unpack what feature engineering really is, why it's so important, maybe more important than we think. We'll look at real-world examples, break down some common methods, and try to understand why people say features are like the soul of AI, how they really dictate how well an AI performs. Sound good?
Sounds great. Let's get into it.
Okay, let's unpack this then. We've got the cooking analogy. So, stripping it down, what exactly is feature engineering?
Simply put, feature engineering is the whole process of pulling out or creating or maybe just tweaking the information that's already in your raw data. The key is making it genuinely useful information, making it easier for the AI model to learn from.
So creating new bits of data, almost, or refining what's there.
Exactly. Creating new variables or features or just fine-tuning the existing ones. It helps the model spot the patterns, the relationships hidden in the noise.
You said making it easier. Could you give an example? Like, how is raw data sometimes? Well, hard for a model. Maybe with dates and times. That seems common.
Oh, dates and times are a perfect example. Okay, imagine you just feed the model a raw timestamp, like 2025 0816 6:30 p.m. To a machine learning model, that's just, well, it's just a string of characters.
Right. It doesn't inherently know that's a Saturday evening or anything special about 6:30 p.m.
Precisely. It has no built-in concept of August or weekend or commute time from just looking at that string.
So the model sees numbers and slashes, but misses all the context we humans instantly get.
Exactly. And that's where feature engineering comes in. We don't give it the raw string. Instead, we transform it. We create new features from it, like maybe day of the week, coded 1 to 7, month of the year, hour of the day. You could even add features like, is it a public holiday? Or is this typically off-peak?
Ah, I see. So suddenly the model can see patterns, like maybe sales spike on weekends or traffic is bad at certain hours.
Exactly. It's not just a timestamp anymore. It's a whole set of attributes describing the situation around that time. Much richer information.
Okay, that makes sense for time. What about something that's already a number, like, say, house size, square footage?
Good question. Yeah, house square footage is a number. It's useful. But is it the most useful way to present that information for predicting price? Maybe not always. Its meaning, its predictive power, can often be boosted if we derive a new feature. A classic one is price per square foot. Simple division, total price divided by the area.
Okay, so combining two existing pieces of data.
Right, and that derived feature, price per square foot, often tells the model much more. It kind of normalizes for size. It lets the model focus on the value linked to location or maybe the quality of the house, market demand, things beyond just how big it is.
So the model can figure out that a tiny apartment in a prime downtown spot might have a higher price per square foot than a huge house out in the suburbs.
Exactly. That's a nuance that just square footage alone might completely miss.
Got it. So it really is like taking that raw ingredient, the whole chicken, and prepping it properly, making it into, say, perfectly trimmed pieces ready for the pan, making the data digestible, but also more informative, more nutrient-rich for the AI.
That's a great way to put it, nutrient-rich.
Okay, so A lot of us, and I include myself here, we hear about the latest AI models, right? These super complex neural networks, deep learning. And you kind of automatically think that's the star. The model is doing all the hard work. But it sounds like you're saying there's more to it, that even the smartest model is limited by what you feed it.
That really gets to the heart of why feature engineering is so critical. Because, fundamentally, models don't eat raw data, they eat features.
Models eat features.
Yeah. Good features are like those good ingredients we talked about. They let the model learn faster, learn more accurately, and maybe most importantly, they help it generalize better. So it works well on new data it hasn't seen before. Without carefully designed features, even a really sophisticated model like a big, deep learning network might just struggle. It might not find the important patterns. Sometimes it might not perform any better than a much simpler, older algorithm if the features aren't right.
Wow. So the model's complexity can't just magically fix bad input.
Pretty much, yeah. The complexity can't compensate for a lack of meaningful signals in the input.
Okay, that's a really key point.
Yeah.
So what happens in the real world when this goes wrong? Or better yet, when it goes right? Can you give us an example where good feature engineering makes a massive difference?
Sure. Let's take credit card fraud detection. That's a high-stakes area, right? Accuracy and speed are everything.
Absolutely. Millions, billions of dollars at stake.
Okay, so if you only give the model the transaction amount, it's incredibly difficult to spot fraud. A $5,000 purchase could be perfectly legitimate, someone buying a new laptop. A $5 coffee could be fraud, part of a testing pattern. The amount itself isn't enough.
Right. Context is missing completely.
Exactly. But now let's engineer some features. Let's add things like number of transactions this card made in the last hour, or the average transaction amount for this card over the last month, or the geographic distance between where this transaction is happening and the last one.
Yeah.
Was the last one in London and this one suddenly in Sydney 5 minutes later?
Okay, yeah, that's a huge red flag.
Right. Or maybe, is this transaction happening at 3 a.m. when this cardholder usually only shops during the day?
Right.
You add these kinds of features, these contextual clues, and boom, the accuracy of fraud detection goes way, way up, often dramatically.
Because the model can now see anomalies, deviations from normal patterns.
Precisely. These engineered features highlight the subtle signals of fraud that the raw transaction amount just hides. It's learning the behavior, not just the numbers.
That makes total sense. It's painting a picture for the AI,
Yeah.
not just giving it a single data point. What about another field, maybe something less dramatic than fraud?
Okay, how about predicting house prices? We touched on square footage earlier.
Right. Not enough on its own.
Definitely not. 2 houses, same size, wildly different prices. We all know that.
Location, 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 and condition, age, school district.
Exactly, all those things. So good feature engineering here would involve creating features like distance to the nearest subway station or major highway, crucial in many cities, age of the house, number of bathrooms, maybe even binary flags like, has it been recently renovated?
Right.
Or something like floor height. You know, in a high-rise apartment building, higher floors often cost more. Better views, maybe less noise.
Interesting. Never thought of floor height as a feature.
Yeah. If you include these kinds of features, the model gets a much, much better handle on the local market dynamics. It can make a far more accurate price prediction. It moves beyond just size to understanding what actually drives value for buyers in that specific area.
So listening to this, it really sounds like you're saying that feature engineering is, well, maybe more important than the actual model you choose. Is that too strong?
It might sound strong, but honestly, in many, many projects, it holds true. What these examples highlight is that excellent, really well thought out features. They can make even a pretty standard off-the-shelf model perform incredibly well, top-tier results.
Okay.
But the flip side is also true. If you have poor features, or just not the right ones, even the most advanced cutting-edge AI model can be completely ineffective. It just won't find the patterns.
So the features are the foundation.
Absolutely. It's the bedrock. You know, data scientists often say that feature engineering can be like 80% of the work in a machine learning project.
80%. Wow.
Yeah, it takes time, domain knowledge, creativity, but it pays off hugely in performance.
Okay, that's incredibly clear. And definitely a shift in perspective for many of us. So if someone listening is starting to think about this, maybe getting into data science, what are the common ways you actually do this? What are the main techniques, the recipes in our cooking analogy?
Great question. There are several common approaches, and you usually pick based on the type of data you have, just like choosing how to prep vegetables versus meat.
Makes sense.
Let's start with numerical data. We talked about income and age.
Right, numbers are numbers, but models might get confused by the different scales.
Exactly. You could have income in the tens or hundreds of thousands and age mostly under 100. If you feed those raw numbers in, especially to certain types of algorithms like neural networks or anything using distance calculations, the feature with the bigger numbers, like income, can just dominate the process. The model might think tiny changes in income are vastly more important than big changes in age just because the scale is so different.
Even if age is actually a better predictor for whatever you're modeling.
Precisely. It throws the learning off balance. So we use techniques to fix that. Common ones are standardization, where you rescale the data so it has a mean of 0 and a standard deviation of 1, or normalization, which usually scales the data into a specific range, like 0 to 1.
Okay, so you're putting everything on a level playing field, numerically speaking.
That's the idea, making them comparable, more palatable for the model so it can weigh their actual importance fairly.
Got it. Okay, what about data that isn't numbers? Text descriptions, categories?
Yeah.
That seems trickier.
It is a bit trickier. Think about categorical data like city names, London, Paris, Tokyo, or product types, electronics, clothing, groceries. A computer doesn't inherently understand London or its relationship to Paris. They're just strings of letters.
Right, it doesn't know they're both major European cities, unlike Tokyo.
Exactly. So we need to convert these categories into numbers the model can work with.
How do you do that without accidentally making the model think, say, Paris is mathematically greater than London just because you assign it a bigger number?
Good point. You want to avoid implying an order that isn't there. A very common way is one-hot encoding. Basically, for each category, you create a new column that's binary 0 or 1. So if your feature is city with London, Paris, Tokyo, you create 3 new columns. Islanden is Paris is Tokyo. For a data point from London, Islanden is 1, the other 2 are 0. For Paris, Paris is 1, others 0.
Ah, okay, so each category gets its own on-off switch.
Pretty much. But you can probably see a potential issue here.
Yeah, if you have like hundreds or thousands of cities, you suddenly have hundreds or thousands of new columns. That sounds messy.
It can be. That's called high cardinality, and it can lead to way too many features, the curse of dimensionality we might talk about later. Your data becomes very sparse.
So what do you do then?
For situations like that, or when you suspect there are meaningful relationships between categories that one-hot ignores, more advanced techniques like embedding are used. Think of embeddings as learning a dense numerical vector, a list of numbers for each category.
A vector, like coordinates in some kind of space.
Kind of, yeah. The cool part is that categories with similar meanings or that behave similarly in the data tend to end up with vectors that are close to each other in this learned space. So the model can capture nuances, like maybe London and Paris are closer to each other than they are to Tokyo in terms of whatever the model is learning, and it's much richer than just zeros and ones.
Wow, okay. That sounds powerful, but maybe more complex to set up.
It can be, yeah. Often used in natural language processing for words or recommendation systems for products or users.
Okay. So we've covered scaling numbers and encoding categories. What about actually combining features, like your price per square foot example?
Right, feature combination or interaction features. Sometimes the real magic isn't in the individual features, but how they interact. Price per square foot is a perfect ratio example. Another one in finance might be debt to income ratio. Combines 2 numbers into a more meaningful metric.
Or maybe multiplying 2 features.
Absolutely. You might create an interaction term, like age income. Maybe the effect of income on, say, spending habits is different for younger versus older people. This combined feature helps the model capture that nonlinear relationship.
So creating a new feature that's literally more meaningful than the sum of its parts. That's quite clever.
It really is. It often requires some domain knowledge or intuition about what combinations might be predictive. It's where the art part of data science comes in.
Okay, but this sounds like we could end up creating loads and loads of features. One-hot encoding, combinations.
Right.
What happens if you just have too many features? Does that cause problems?
Oh, absolutely. It's a critical point. While good features are essential, having too many can definitely hurt. It's often called the curse of dimensionality. More features means exponentially more data needed to cover the space. Models can become much slower to train, and worse, they can start to overfit. They learn the noise and random quirks in your specific training data instead of the real underlying patterns, so they perform poorly on new data.
Right, like trying to draw a super complex line that hits every single data point perfectly, but misses the overall trend.
Exactly. I remember a project, we ended up with thousands of potential features after initial engineering. The model was just lost, completely unstable.
So what do you do? How do you slim down the features?
That's where dimensionality reduction techniques come in. Things like PCA, principal component analysis, or TSNE, which is often used more for visualization but captures local structure. These methods try to find a smaller set of new features or dimensions that capture most of the important information, most of the variance from the original high-dimensional set.
So compressing the information down to its essential components.
Essentially, yes.
Right.
PCA finds linear combinations of the original features that explain the most variance. It helps reduce redundancy and noise. It makes models faster to train, often more robust against overfitting, and sometimes the resulting lower dimensional data is easier for us humans to visualize and understand too.
Okay, so it's about finding the signal amidst the noise and simplifying.
Exactly. So all these processes we've talked about, scaling, encoding, combining, reducing, they're like the different steps in careful cooking, aren't they? Chopping, marinating, seasoning, maybe reducing a sauce down to concentrate the flavor, even plating it nicely. Each step makes the ingredients better suited for the final dish.
That's a great way to tie it back. Okay, this has been a really fantastic journey through the what and the how of feature engineering.
Yeah.
To kind of pull it all together now, you mentioned earlier that feature engineering is seen as the soul of AI. What does that really mean for how it relates to the AI model itself? If the model is the kitchen tools, how does this soul interact with the tools?
Yeah, connecting it back to the bigger picture. If the model architecture, the specific algorithm, the neural network design is like the set of kitchen tools you have, a basic blender versus a high-end food processor, a simple oven versus a sous vide setup. Those tools are important, definitely. They determine how you can process things. But the features are the soul. They are the quality ingredients and the chef's skilled preparation. They determine the actual flavor, the substance, the essence of the final result.
So even the fanciest AI tool is useless without good ingredients prepared the right way.
Pretty much. A state-of-the-art model-fed garbage features will likely produce garbage results. It can only work with the information it's given in the form it's given.
Which really brings us back to that question we started with, doesn't it?
It does.
Why can the same raw data lead to such different results when different people train models?
The answer, in large part, lies right here. It's because different people will apply different feature engineering strategies. They'll have different ideas about which features to create, how to transform them, which combinations are important. One person's prepared ingredients might be much better suited for the model and the problem than another's.
Even if they use the exact same model algorithm later on.
Exactly. It highlights how much human insight, domain expertise, and just plain careful work applied to the data itself drives the success of AI. It's not just about picking the fanciest model.
It's a strong reminder that there's still a lot of human intelligence required in artificial intelligence.
Absolutely. The quality, the relevance, the thoughtful construction of your features, that directly impacts how well your model learns, how well it generalizes to new situations, and ultimately how accurate and reliable its predictions are. It's where understanding the problem and the data deeply really pays off.
Okay, so today we've taken a real deep dive into feature engineering. We've looked at what it is, why it's so incredibly vital, often more so than the model. We've walked through some common methods like scaling, encoding, combining features, and really tried to understand this idea that model architecture is important, but features are the soul.
Yeah, it's about giving the model the best possible view of the underlying patterns, transforming raw data into actual intelligence.
So here's a thought for everyone listening. As you go about your day, maybe you see a report at work, read an article, even just notice things happening around you. Think about the raw data behind it, and then consider what features might be hidden in there. What information could be extracted or transformed to reveal something new, some surprising insight, or maybe even help solve a tricky problem.
What connections are just waiting to be uncovered with the right kind of preparation? Every piece of data has potential.
A great thought to leave us with. We'll continue this AI journey in our next deep dive. We'll be tackling model selection and comparison. So once you have your features, how do you choose the right kitchen tool for the job? Which recipe, which model is best? Get ready for supervised learning S03EP04, the secret of exam question banks.
Looking forward to it. Choosing the right algorithm is definitely another crucial piece of the puzzle.
Thanks so much for joining us on this deep dive today. If you found this exploration helpful, please do subscribe so you don't miss our next one.
Thanks for listening.
We'll see you next time.